morning, beautiful people, or good afternoon, good evening, whatever time it is when you're watching this. My name is Bins, and welcome back to the Shapez BEASTMAM series. My friends, we've turned a page on our journey. After having analyzed this machine's clock mechanism with an electron microscope, it's time to shed a light on the next step in the decoder's algorithm. Chapter 4C will be all about the so-called remainder, a term I give to the collection of quadrants that's complementary to whatever the clocks are outputting. Now, I would like to remark that the clock is the biggest topic in this series. Since the clock is truly the beating heart of this factory, I deemed it necessary to talk about it in quite a bit of detail. But since the other parts of the factory all depend on the clock, it means the upcoming chapters and sub-chapters will generally consist of fewer videos. So we've dealt with the biggest chunk and onwards we move. In this first episode about the remainder, I would like to talk about the theory of a subtraction module. A subtraction module is a kind of module that is going to take the floating pieces that come from the clock and quite literally deduct or subtract them from the target shape. In other words, this is all about finding out which flat, non-floating pieces we need that, when paired with any set of floats that comes from the clock, builds the final shape. The other half of the puzzle, right? Now, a subtraction, like for example 8 minus 3 is 5, well, that's easy, right? We all learned how to do that in elementary. But how do you subtract one shape from another? That's not quite as trivial. Now, remember the layer correction module I showed you in last video? Look, it's a flag of Japan. Well, the principle is actually the same. We will need a main input on one hand and then a side input that will act as a kind of filter for the main input. The difference is that this time we won't run one and the same value into both input lines, but we will actually have two different inputs. The first observation is that we can only do this for individual layers, so the inputs need to be flat pieces. At least that's the only method I've been able to come up with. Now, I will take advantage of this time to issue a word of advice. When you start creating these modules that require you to chop up the shapes into layers and the layers into quadrants, then please do yourself a favor and use test values that adhere to some kind of system that works for you and that you find easy to remember. For example, if I have to pick a set of 4 shapes, I will always work with the sequence circle, rectangle, star, windmill. And if I need a set of color values, I will usually go with either red, yellow, green, blue, or otherwise red, green, blue, white. Okay? So when it comes to setting up modules and testing them, I might end up using a shape like this one, for example. I use circle, rectangle, star, windmill in accordance to the layers 1, 2, 3, 4, and I use red, green, blue, white in accordance to the corners, top right, bottom left, and top left. Okay? Now, why do I do that? Well, because it greatly helps me keep a clear head and I keep a better overview of my machines, and I'm certain it will do the same for you. For example, if I find an isolated white star quadrant value somewhere on some wire of some module within the big cluster of wiring modules that is my machine, then I will immediately know, okay, this wire carries the top left quadrant of the third layer of my shape, and not only that, it's currently rotated 90 degrees clockwise. Since it's a star, and I use that exclusively on the third layer, this must be a value that's that represents the third layer, and it's white, which I exclusively use for the top left quadrant. And the fact that it appears in the top right instead of the top left, well, that means that this value is the result, it must be the result of a 90-degree clockwise rotation earlier in the machine. And at some point, I will still require a 90-degree counterclockwise rotation applied to this before I obtain the final shape, right? I really advise you to do this if you don't, because it will be of great help. We're only human after all, right? So come up with a system that works and that you can map to certain layers or certain orientations, you know, a sequence that you can connect one-to-one with a given value that you can recognize if you see it isolated somewhere in the factory. And having said that, we can get back to today's topic. Let's build a rudimentary subtraction module together. And in order to do that, I'm going to start by following up my own advice and take a shape, for example, with circles, a red circle in the top right, a green circle in the bottom right, a blue circle in the bottom left, and a white circle in the top left. Okay? So the first thing we're going to do is we are going to chop that up into quadrants, because this is a mechanism that only works on individual layers. So there we go, left, right. And then I think to make life even easier on ourselves, I am going to do it from left to right, top right, bottom left, top left. Okay, so we go in clockwise fashion. So the first thing I'm going to do is rotate this 180 degrees. Yep. And then we rotate that clockwise once, like so. So we get the red circle, and you can already see it's rotated, right? So keep a clear head. This is now in the top left, but it represents the top right quadrant of the actual shape. That's how that works. So we put that there, we put that there, and then I think we can copy this. Can we? Or do we need to rotate that differently? Yes, we do. So let's do not a clockwise, but a counterclockwise rotation, like so. Right? That's it. That's going to be our bottom input. And then we are going to do the same thing, but we're going to be coming from the side, like so. Okay, let's get rid of this because I find it annoying on the edge of the screen. There we go. So now we have the same thing twice, and in order to match these signals properly, I'm going to also start off using the same shape so we can connect the wires to one another. And now the only thing we need to do actually is, let's say we're going to use this as the filter input and this as the main input. So the only thing we need to do is connect this there, white to match with white, blue to match with blue, green to match with green, and then finally red to match with red. Let's connect that up. All right, there we go. And now the final thing to do, no, the second to final thing is rotate these pieces because they've been rotated. We want to bring them back to their original positions. So again, keeping in mind the system, we know that red is the top right and we've rotated it clockwise once. So now we need to rotate it counterclockwise once, right? Except I chose the wrong unit. Let's try that again. And I also misspoke. 1 counterclockwise rotation, so... Wait, am I blind? Oh, right. Right. We rotated it 180 degrees here, 90 degrees clockwise here. So if we rotate it 90 degrees clockwise again, that's when we end up with the original position, right? Confusing myself a bit here. So that's that. And then here we need to do it like so. And so. Okay. And then the final thing we can do is stack those together. Or combine them, I guess, but I'm going to take advantage of the smart stagger that comes with Wires Plus. Like so. And like so. There we go. That's what we're gonna do. And now I'm going to make this unit a bit smaller, a bit more efficient. Alright, that's a bit better. And now, since this is a subtraction module and not an addition module, what we are going to do is we are going to take the values that come from the bottom, and whenever a value is given, we want it to not enable the transistor, but to disable the transistor. So we still require a few NOT gates, right? 1, 2, 3, 4. There we go. And that is our subtraction module done. Now, what can we see? This is the main input, and this is the input that we are going to subtract from that. So since this is the same value, the output is going to be nothing. This is like saying 4 minus 4 equals 0, right? That's what's going on. If I take this away, like so, then we will get all of the 4 quadrants. This is like 4 minus 0 equals 4, right? Now let's see what happens if we take something like this. We are going to subtract just the red top right quadrant from it. You will see that it is missing. It will be missing in the output. And if we do another one like this, for example, the remainder will be white and green. So I can keep demonstrating this, but you get the principle, I guess, right? So, all right, that's how that works. And I think that's also a wrap for today. I kind of wanted to go over this how this kind of module works in isolation first, how you can set it up, so that in upcoming videos, we can have a look at how that has been applied within the BEASTMAM, because otherwise, you know, there is so much wiring going on, it might get a bit confusing to isolate those parts that we actually want to focus on for this episode and the upcoming ones, right? So this topic of what the remainder is. So I wanted to look at this in isolation first, and then in upcoming videos, we can have a look at how that is applied. Now, if you like this video, please leave a thumbs up or a nice comment. That's always greatly appreciated. And if you're curious about what else I've got lined up for you in this series, well, then consider subscribing to the channel. And with that said, it's time for me to wrap up and wish you a nice day. I've been Bins. Thank you very much for watching. Take care. Bye.